This is our optimization project with Carlton, Sashank, and Avi. Our project is on large-scale random coordinate descent methods for optimization problems with linear constraints. We will decompose this clumsy title into 3 components. So we will start talking about the optimization problems we care about, and then how we solve them using random coordinate descent, and finally how we scale our method to large scale. So in like linear less terms, we will start talking about the problem formulation motivation and then our method, and then the results like theoretical and experimental results, and then parallel variance. And finally, we'll talk about some extensions we are considering. So let's start with problem formulation. The class of problems we care about is the decomposable objective functions with linear constraints that tie all your variables. So our objective function is in the form f of x that's a sum of fi xi, where each xi is an n-dimensional variable, and you have a linear constraint, a general linear constraint that ties all these variables. We have an assumption that the constraints are kind of like nice in terms of number and or sparsity. What nice means will become clear later. We assume that fi has a known Lipschitz Lipschitz continuous gradients, and the Lipschitz constant is known. And we assume that you have a first order black box oracle for each fi. In a distributed setting, we assume that variables are distributed across nodes, where each node has an access to a variable and the corresponding oracle for the corresponding functions. And we assume that the communication between nodes is restricted, so not all nodes can communicate to each other. And this actually comes in practice. So for example, if you have a cluster of 2 multi-core machines, and you want to model the fact that you want more communication to happen within machine than communication across machines, because communication across machines is more costly. In a more general sense, we assume that you have some distribution over edges that basically governs how often you want to communicate between each pair of nodes. So why bother about this class of problems? Well, this class of problems, where you have decomposable objective and coupling constraints, actually appear in many applications. So for example, in resource allocation, you have a finite amount of resources, and you want to allocate these resources to multiple consumers. Then you want to maximize the sum of utility for each consumer, but you don't want to over allocate your resources, and so you have a sum constraint. In general planning, your variable might represent like a policy that each agent is taking, and you have some constraints that couple these policies together. Also, this problem appears in locally linear embedding. If you add additional structure constraints, or in general in linear programming, because you can look at the objective of, if you have a linear objective, you can look at it as like a separable objective. And if the constraint matrix is nice in the terms that we will define later, then you can use this method.
Except for linear programming, your Lipschitz constant will be 0, so maybe you don't want to use linear programming as an example. But the resource allocation is a good example, because there's a lot of knapsack-like problems, and there are a bunch of constrained knapsack-like problems. I once saw a list of hundreds of such separable objectives with some constraints. So now that you mentioned the word resource allocation, I got reminded of that. So I mean, I can tell you, because I think you asked me about more practical examples. So I think there's a large body of examples of this thing hiding. And for the class, I can mention that if it is separable and has linear constraints, and actually x is constrained to be an integer, if f is convex, you have linear constraints, A is integer matrix, and x is constrained to be an integer. for some special cases, even that problem can be solved in polynomial time, given good structure on A. So it's a nice class of problems.
Okay. So that's like why you bother to solve this problem. Why bother develop a new method? So you can think of applying like several alternatives, like projected gradient descent. In this case, you can take the gradient with respect to each xi, but then to maintain the constraint, you will need to apply like a global projection step, which is not very appropriate for a distributed setting with communication constraints. ADMM is another alternative, but it's not inherently parallelizable for general general A matrix. You can apply coordinate descent with indicator functions, but in our case we have coupling constraints, so you can't update individual variables, otherwise you will lose feasibility. There's randomized coordinate descent proposed by Newcar et al. In 2011. And it solves the special case if the constraint AX is equal to 0 is a sum constraint, sum xi is equal to 0. But we want to extend that to a general linear constraint. Okay? Cool. So let's move to our method. The solution outline is the following, that we will start with a feasible point, and let's say x is equal to 0. And to maintain feasibility, we will update pairs of variables. This is like SMO style algorithms. And let's suppose that the constraint is in the form sum ixi is equal to 0. Then we can derive an update. And the idea is if you update x1 with the difference d, then x2 will be updated with minus d to maintain feasibility. And so what we are going to do is that we will reduce our general case ax equal to 0 to this special case. So the reduction will be as follows. We will assume that the A matrix is divided into blocks corresponding to individual variables in our collection. And so our constraint will be sum ai xi is equal to 0. We will define yi to be equal to ai xi. And we require that we must be able to recover xi for a given yi. And that happens if ai is either has a small number of rows, or it is sparse such that the number of non-zero rows is smaller than the dimensionality of xi, very equal to. If this is the case, then we can write xi in terms of yi. So xi will be equal to ei pseudo inverse yi plus some component in the null space of ai. This null component will be represented as null ai. Null ai is like a set of columns that span the null space of ai, and zi is a free variable. And so our objective will become a function of yi and zi. So we can rewrite our optimization problem as minimize gyz. It's a decomposable function subject to a sum constraints. But we have, in addition, a set of free variables, z.
How much time does it take to get the null of AI?
So null of AI, A itself might be large, but each individual AI is assumed to be of reasonable size. And so if you do an SVD, you can get the pseudo inverse. So we assume that we can.
Typically, in your examples, what sort of size I should keep in head for Roughly, just to orient myself.
So it's the maximum. Maybe if you have like 1,000 constraints, and let's say you have each variable is of dimensionality. 1,000 constraints times 1,000 times 1,000. If you can do SVD for 1,000 times 1,000, yeah.
There's one thing that this has to be done only once. It's not.
Yeah.
So anything you can take the SVD for once, you're good.
Yeah.
So,
Sure. I was just trying to roughly have an idea
Okay.
how big I should
And-
train this matrix to be.
I mean, for a lot of these things, you can take an approximate SVD using like methods of prop and stuff learned in the class.
Do you count?
So,
So just for clarification, so if xi is a scalar, here yi is going to be a vector.
So we ask if xi is a scalar, in this case, yi is equal to ai xi would be like over constrained.
So it's a vector.
So xi is a vector and yi is a vector.
So if xi
Yeah.
is a scalar, yi is also a vector.
Yes, that would be the case, but that case won't. I mean, that case will most probably violate our assumption that yi equals ai xi must be feasible. Because it will be an over-constrained system of equations.
AIXI cannot happen for a non-scalar
Yeah.
yi.
Yeah.
So essentially you're growing up information here, right? Previously I only had one xi, and now I have a function yi to accommodate.
So that's
it's the other way around almost.
yeah.
So you're taking like, you have a bunch of constraints and you have one yi for each constraint. You see, so this is the, when I apply this vector to my input, I get this yi at the end, and I'm going to sum these y's to get my final. I want all of them together to sum to 0. So instead you're sort of taking, for each constraint you get one yi, so you get the number of yi's equal to the number of constraints. And those are mapped back to vector size x's.
Yeah, I'll comment on that also in the question answer time. Okay. So given that, we can upper bound the difference in our objective function if we pick a pair I and j, and basically change yi by alpha I and zi by beta I, and the same for j. We can upper bound the difference knowing the Lipschitz constant using this bound. And we know that alpha I must be equal to minus alpha j. We just minimize this upper bound and get these updates. And so we do the SVD once, and then we can work using y and z, and the mapping is available. So we have this convergence theorem that basically in expectation, the difference between the current objective function and the optimal one scales sublinearly. So it's 1 over k.
What is the expectation over?
The expectation over randomness. Because here we pick random. Random pairs. So the expectation is over the random pairs that you pick.
The randomness enters.
Yeah.
You
Yeah.
try picking
Yeah.
arbitrary pairs. And there is no bias in which pair is picked uniformly.
And that will appear in this Laplacian. So the probability of picking each pair will affect this Laplacian. But in our experiments, we pick pairs uniformly, like subject to the communication constraints. So if you have like,
What does it mean, uniformly subject to constraints?
So basically, uniformly on edges.
yeah.
Okay.
On the
So you have some available edges. We pick from these edges uniformly.
So the convergence will depend on the eigenvector of the population.
Yes.
Think about it as like, because you're updating pairs, you're sort of propagating information between the variables. And depending on which edges are present, depends on the rate at which information can propagate throughout the variables. So the
Yes.
complete graph, for example, uniform at random, you get very little propagation. You have a red graph where the span of the set is very high, isn't it a long time to information problem?
Yeah.
That comes in sort of the diameter of the system or the
Yeah. So like z variables are unconstrained, and so they don't depend on the graph. They depend on how much you sample edges adjacent to that variable. And so the more you update the variable, the more basically you converge faster in z. For y, it depends on the graph, and so we ran experiments on multiple graph layouts. And as we can see, convergence significantly depends on like how the graph is connected.
Iteration here means number of samples of edges?
Yeah.
Yeah, because that
But-
corresponds to an
yeah.
update.
So yeah. So basically, chain and ring are chain and ring are like very similar. Binary tree is much better, and like clique is doing the best.
Are they ready for
There are only 3 lines.
Yeah.
two of them.
Well, no. So chain and the chain and ring are the same. Yeah, very simple. Okay, so there's the other thing. We have mapping between variables, and this map depends on AI. And so the Lipschitz constant that's given by the oracle is not the Lipschitz constant in terms of y and z. And so how the AIs are well conditioned plays a significant factor. And so if A is well conditioned, you can end with a few iterations, but the number of iterations increases fast as A becomes fully conditioned. And so we investigated the preconditioning of A's. It turns out actually like simple preconditioning using SVD can give very nice improvements. But this requires doing SVD of the entire A matrix. And so now we are investigating ways either like to approximate that SVD using random projections and so on.
You basically just have to find the span of the thing. So
Yeah, okay. So rather than pick, now moving to larger scale, rather than pick one pair, we can pick non-adjacent pairs. And because the optimization, the function is decomposable, then these updates won't conflict. And so we tried that, and we got like nice speed up as we increased the number of processors. Yeah, we tried that on like a C++ implementation. We also have an MPI distributed implementation, but we didn't manage to experiment with it. Like we didn't get the hardware yet.
Can I download your implementation?
Sorry?
Is download part of the project submission? Like is the implementation being released for public consumption or not before you publish the paper?
Well, we would like that, but maybe not before Friday. I mean, in the future, not like. I mean,
Because
if you.
ultimately,
Yeah.
for many of these things,
Mhm.
having a publicly available implementation is a very important part of the whole
Mhm.
contribution.
Yeah, we would want to have that, but it's just like not currently ready for release. Okay, so the two extensions we're investigating is asynchronous updates, because if you want to ensure that the pairs you pick are disjoint, you need synchronization, which is bad for distributed systems. And so can we just let the processes go and recover in case of conflicts? And the point is, suppose you pick like pair 1, update this 1 with D and 2 with minus D, and do the same between 2 and 3. If you accumulate the increments rather than like override the values, so you decide D and minus D, and then whatever is inside 2, you add minus D to it, even if it has been updated by another processor. If you do that, then you will maintain consistency. You will maintain feasibility. But you may not maintain descent. So we need to investigate like the conditions to make that work, like hog wild style methods. The other thing we are investigating is what if we have a non-smooth part? And it turns out that if we look at this formulation, we actually have two functions for both which we can do the Plox operation. And so why don't we just try like a Douglas-Sackford variant on this setting? Yep, so separable objectives lead to efficient parallelizable algorithms, even in the presence of coupling constraints. Communication structure and conditioning of constraints significantly affect convergence. Thank you.
Questions?
I hope somebody else in the audience also asks questions.
Yeah.
So suppose I'm going to increment another element, say ADM, and I can do randomized element, where with each iteration I'm going to sample one of the fi. And I think if I do that, I will get a convergence rate in the expectation one of the root case instead of one of the root case. So is there any reason you can get a faster rate here? So essentially, you get one of the k rate in expectation without assuming any external maximum.
Other than decomposability, yeah, we don't.
So
yeah.
for the full ADMM, even if you sample the separable part, one of the punishments might come from just solving full linear system with A at each step. You want to avoid that. Separability by sampling, yes, that gives you 1 by k for strongly convex functions.
Yeah, we didn't really assume any.
No, they didn't.
That's why I want to find a faster rate.
Yeah, means it's a good question. I don't exactly remember what faster rates people have studied for just ordinary coordinate descent also. Because I know Nesterov has in his paper some faster rates, but it's not also clear if empirically those things are truly faster. But in the one thing, nicer thing is that you don't have to handle the full A matrix at every iteration, which can be quite a nice thing. And another important thing contrasted to ADMM, which I think, I don't know if you guys are you're exploiting that when speaking about it, but it's important to know. In some applications, it's important to maintain exact feasibility at all times. ADMM will never maintain exact feasibility, only in the limit. So it depends if that's physically tolerable or not. So it really depends. Means even but it would have been. Do you have actual runtime experiments against something like ADMM in your report?
Work in progress.
It's the first question that everybody has, so it's good to at least have one thought which answers that.
We have to have another report. We don't have.
Okay, sure.
So before the other groups are having you have like two condition numbers. One is the condition number of the graph connections. The other is the condition number of A, which is A. How does these two like factors interplay? Are both this dependence on condition number like exponentially increasing?
It's not exponentially,
but it moves pretty fast.
Okay, so yeah, so like a worst case scenario would be that the Lipschitz constant in Y would be 1 over the square number of the minimum singular value of A, the minimum non-zero singular value
of
A.
the minimum non-zero singular
value. Yeah.
You could show a precondition that you can push that towards like 1 over root n.
Yeah.
So the root of it cancels and it goes up after that.
Yeah, but you precondition the graph structure. 'Cause, yeah,
Well,
that's a
the graph
physical
structure,
system.
that's a constraint, yeah. So the point of the graph structure is, like something imposed, and what you need to do is, I mean, it's like you choose the probabilities based on communication constraints and or communication costs, and the theorem will give you how fast this will, how fast the convergence will be based on these probabilities. You can, in principle, optimize for, you can optimize to minimize the norm in the theorem. You can optimize over the probabilities.
Okay.
And actually, the new card actually proposes like a suboptimal way of choosing probabilities to guarantee some norm.
Most expenditures is your friend.
Yeah. Yeah, if your matrix A is like SDB. All right, thanks. Nice work.